video will be a crash course to capacitors. One can go to great lengths when describing the physics behind them, but I'd like to keep this one practical because I think that will serve you best in your homework and also your work later in your career, I think. So what is a capacitor? Capacitor is a device that can store electric charge. Usually it's constructed by having two surfaces. The most simple configuration is two parallel plates. And the charge is stored because there's a gap between the two plates. The charge is gonna cross the gap because there's no conductor there. And these charges will build a voltage or potential difference over these two plates. And if we have charge Q here and charge minus Q here, that's always the case. If we have charge Q here, we have the exact amount on the opposite plate, minus Q. And it's been found that these two quantities, the charge on the plates and the voltage difference between the plates, are described by this expression. The charge on one plate, or the magnitude of charge on one plate, equals something called capacitance of the capacitor times the voltage difference over the two plates. This equation tells us that if we want to store some amount of charge, but we want to keep the voltage on practical levels, it means that the bigger the capacitance, the more charge we can store. So the capacitance is, in fact, the capacity of the capacitor to store charge. And it depends on the physical parameters of this capacitor, the shape and size of the plates, or the configuration in general, and what material is between the plates. It necessarily doesn't have to be empty or air. It can be some kind of dielectric. If we want to calculate the capacitance of a capacitor, we can do it in the following way. So the capacitor, or the capacitance, will be Q over V. And if we know the amount of charge that we have put here, then it's left us to determine what is the voltage difference between the two plates. And we know that the voltage can be achieved by, okay, let's call this plate A and plate B, by integrating the electric field as we move over the gap along the path length. So if we want to solve the voltage V, we have to analyze what is the electric field in this particular capacitor. As you know, for a parallel plate capacitor, the electric field is constant, in fact. And if you evaluate this integral, we get an important result. The capacitance is epsilon O times A, the area of one of the plates, and D, divided by D, which is the distance between the two plates. So for a parallel plate capacitor, if we want to make the capacitance high, we can either increase the size of the plates or decrease the distance between the two. Another common configuration for a capacitor is something like this, cylindrical capacitor. This is in fact a coaxial cable. So there's a conductor in the center, and then there's some kind of dielectric, and the outer shell is also a conductor. So there's electric field in the radial direction. So if we call this the radius A, and the radius of the central conductor, that's RB. Oops. If we evaluate this integral over the electric field, we get the capacitance of a coaxial cable. So this would be 2 pi, let's make it better, 2 pi epsilon 0 times L divided by natural log of the ratio of the two radii. One should note that when we are charging these capacitors by, for example, placing a battery between the two plates, the charge doesn't build up instantly, which means that the voltage either doesn't build up instantly. Sometimes that is good, sometimes that is bad. For example, the case of the coaxial cable, we see that the capacitance is larger the longer the cable is. L is the length of the cable. And if we put a signal in this conductor, it takes some time for the signal to build up, and which means that the signal cannot be really, or there's a limit how rapidly the signal can change, and that in fact limits the data transmission capabilities of these traditional copper cables. And if we want to go faster, we have to switch to optical cables. Then again, on the other hand, the slowness of building up the charge and building up the voltage can be a good thing as well. So in most electric circuits, we don't want the voltage to go high instantly, because that would usually lead into high voltage spikes. So having capacitors in the circuits, we can add slowness to their functionality, and by those means we can protect the rest of the circuit. I should note that the capacitance of the capacitor is also the measure of its slowness. So if you have a large capacitance, it takes a lot of charge to build up the voltage on the capacitor. And that is because the rate that we can supply the current or the charge is limited. And that means if we want to bring in a lot of charge, it takes a long time. The most common environment where you will find capacitors are electric circuits. So let's see, what do we do with them when we have to calculate the total capacitance of the several capacitors. This arrangement here is called the parallel. So as you can see, all those three capacitors are in parallel, which means that there's the same voltage which is provided by this battery here, the positive terminal, the negative terminal. It is the potential difference over each of these capacitors, which in fact means, so if you want to replace these three capacitors by a simple capacitor in this sense, so here we have our battery, instead of those three, we have only one. Here's point A and here's point B. So we call this the equivalent capacitor. And when these capacitors are in parallel, the equivalent capacitance is simply the sum of all of them. You could have as many as you like, and this would be the same expression. The situation is a bit more complicated when the capacitors are in series like this. In that case, the equivalent capacitor, which would look like exactly like this, would be calculated from the following formula. 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. So finding the C equivalent requires a little bit more effort than in the case when the capacitors are parallel. This arrangement is called series or capacitors in series. Often, however, in real circuits, you don't see more than maybe 2 capacitors in series. And let's see how we can have a little shortcut with those. So in that case, the C equivalent would be 1 over C1 plus 1 over C2. So if we solve for C equivalent, we get 1 over C1 plus 1 over C2 just by flipping the whole thing over. And now we multiply both numerator and denominator by the product C1, C2. So we will get C1, C2 divided by C1, C2 divided by C1 plus C1, C2 divided by C2. So here the C1s cancel, here the C2s cancel, so we are left with their product on the top and their sum in the bottom. So this is a handy little trick that you could use. And let me box it as well. A word of caution, this result cannot be applied blindly by saying that for 3 capacitors it would be C1, C2 times C3 and then add C3. Well, now that I let the cat out of the box, I might as well write it out. So for this particular case, when we have 3, the equivalent would be C1, C2 times C3, and then all the combinations of 2 we can pick. So C1 times C2 plus C1 times C3 plus C2 times C3. The fact that we are storing charge in capacitors means that we are also storing energy. And that's one of the applications of capacitors. They act like small energy containers where the charge can be extracted rapidly. So what is the amount of energy stored in a capacitor? We call it, well, in fact, it's the potential energy stored when these 2 charges are some distance apart. But the actual expressions for the energy in a capacitor can be stated in several forms. So, for example, it can be Q squared over C, and the other variations come from combining this expression or we can also express it 1 over 2 c times v squared, or 1 over qv. Depending on the problem, one of them is easier than the other, depending on what quantities we know. I already mentioned that the medium between the two plates doesn't necessarily have to be air or vacuum. It can be a dielectric, and that is in fact the most common construction of a capacitor. So between the two plates there is some non-conducting material, and this is done because the capacitance of such a capacitor is higher than the air-filled or vacuum capacitor by some factor k, where k depends on the material, but it's always larger than 1. So with the suitable material selection, we can ramp up the capacitance of the capacitors, usually quite significantly. That was the 101 of capacitors, and next let's do some example exercises to apply this knowledge. In the first